All right, so Hacks didn't skip badminton. What's even the point? What do you do in badminton? Well, first of all, why do you need to take a badminton class in college?
I'm so curious about that they require an HHP class. I'm an adult. I think I can decide if I want to take badminton or not.
Yeah, I get it.
It's just ridiculous.
I mean, you got to look at it from a couple of different lenses, though. And I mean, this is tough. So first of all, the university has the teachers that are teaching these HHP classes. So, these people want to make a living, right? But on the other hand, you guys are paying expensive tuition. Do you really want to dive? So what is it, badminton, a 1 credit hour class?
Yeah,
Okay, how much does 1 credit hour cost?
$1,000.
Is it $1,000? Is that what it is? Okay, so you're paying $1,000 to take a badminton class.
Yeah, I have to.
I mean, that's just dumb.
At least theirs is 7 weeks. I paid $1,000 for 1 weekend of rock climbing.
Or
It's like criminal.
there's a walking class. That's
Yeah.
1 credit.
It's true.
For the 2 credit.
I think my wife took a class in.
Just to walk.
My wife took a class in college on relaxation.
Was it like
Frankly, she needs it.
They teach her how to meditate and everything.
I think so. I think like they think usually classes when the weather was bad, they just sat in the classroom and just sat quietly. And then when the weather was nice, they just said, go for a walk. You can come back if you want.
It's not just Concordia, though. Like, Purdue University has a wine tasting elective class.
That's worthwhile.
Yeah. But that it was hard to get into.
Yes, I don't hear Dover complaining about that. look. Some courses are reasonable. Some courses are reasonable.
Bowling, which was great because they make you go out and go bowling at one point, like separate from class.
But it's not great. It's
You
just
have to
so.
pay- you have to pay for the bowling.
We did.
Okay, that's not.
Okay, so you had to pay for the class and you had to pay for your bowling?
Yes.
For one session.
One session.
Oh, that was like an outside. That was like an assignment.
It was board bowling.
So in a bowling class, you had an assignment to go bowling.
Yes. The best part about it was is that we could go out and drink because Abe, the married one, couldn't drink because he was under 21 at the time.
I don't even understand it. I mean, you could make the same argument for computer science in general. Like, if your major is computer science, wouldn't you rather? I mean, I get this group excluding, because you guys don't care if you learn anything. But generally speaking, wouldn't you rather have extra computer science classes to make you prepared for industry
100%.
rather than having to take, like sociology?
Or basic math.
Well, you do need basic math. I would argue you need more math for computer science than we require you to take. But the reason we've dumbed it down is mostly for people like you. And you. And
I did fine in
a
math.
little bit you.
I do just fine in math courses.
Really? Well, what's just fine? You have low standards.
Like A's and B's.
Well, B's not just fine. B's basically failing.
This is the dude that got married twice over the weekend. So.
You got married twice on the weekend?
No, I got married once and divorced twice.
Married once and divorced twice. That's pretty witty. I'm surprised you came up with that so quickly. All right. So now that we've ripped on the entire curriculum, let's keep going. Okay, so we're not supposed to have a quiz. We already have one that you guys failed.
No.
Yeah, I think like 6 people got it. Not 6 people. I think 4 people got it right, and then like maybe another 2 or 3 like didn't completely miss it. That is, they didn't get the 30%. They got like a 50. And there might have been 170 that was just kind of a gift. And then everybody else got like, they might as well have just put their name on it and drawn a smiley face. That would have been a closer answer. You guys are pathetic. All right, so we talked about date time, kind of a couple different ways of looking at this on Unix systems. So we can look at it from a human perspective as well as how much CPU time it got. Both of those might be of interest. Did we start talking about client-server architecture?
Yeah. You were
Okay.
talking about McDonald's.
Okay. Yep. So this idea, typically we would think about client-server as being more of like, okay, well, like web servers talking to web browsers, that kind of stuff. But really, this client-server architecture exists at micro levels inside of all operating systems. We see it in Unix all over the place, where we have child processes that have to communicate, talk to, request information from other processes, maybe their parent process, that kind of stuff. So that creates that same kind of model of having a client asking a server for information, and then that server being able to send that information back. And we have tools underneath that for inter-process communication and things like that to pull this off. So I think it's easy for people to assume client server has anything to do with the internet. You know, they like, oh, well, it's actually a server someplace else, and I have my computer here. We open up a TCP IP socket someplace else, whatever. It doesn't have to be that complex. It could just be one program talking to another program on the same computer. Okay. So real-time applications, I like to kind of refer to these as relative real-time, because real-time is kind of in the eye of the beholder when we're talking about operating systems in general, because our CPU is trying to fake us out, fake our end users out, and that doesn't mean that things are happening in real time as long as we perceive they are. All right, that's the punchline. Some things obviously are more important to be low latency than others. So, for instance, aircraft navigation. You know, we probably don't want to check the area for other nearby aircraft every hour. Might want to have every couple of seconds a ping and that type of thing, or more often, but certainly not every hour. Yeah, whatever. Okay, so the proc file system. So the Unix file system has this virtual file system within it that provides an interface to the kernel data structures in a form that looks like files and directories. So again, just like our quiz from last time, everything is a file. Right? So even our system services, the things that are exposed by the API for the operating system, look like files. And when we need to perform something, especially at the kernel level, we can access that file directly. A good example is there's historically, if you needed to get random data to fill an array up or something like that, there is a system call in Unix operating systems called dev null. And dev null is, it looks like a file. It's in our devices, so it acts like, it's kind of set up as if it's a device. But it's a virtual device, and literally it just spits out random zeros and ones. You say you can read 100 bytes from it, it will just give you 100 zeros and ones. It's just randomly streamed. That's what dev null does. So this idea of having functionality built into virtual hardware that looks like a file is very much a POSIX Unix thing. Okay, now, like I said here, the proc file system, this is a Linux-specific thing. This isn't part of that POSIX standard, but Linux has adopted this, so you would find this across all Linux distributions, or most Linux distributions. And I think FreeBSD has a proc file system. But just like, nothing says it has to, because it's not a POSIX thing. It's everything's a file is a POSIX thing. Proc is hey, we kind of like that idea, so here's some extra bells and whistles that leverage that everything's a file thing that you might find handy. All right, so system calls. So at the end of the day, historically, we've talked about this idea of an API. So when I say API, what does that mean to you? I wrote down here what it stands for, Application Programming Interface, but what does an API mean to you in terms of solving problems? Go ahead.
Something pre-made that solves a specific problem.
Okay, so definitely something pre-made. Who made it? Who would provide an API?
Another company, or just somebody that wants you to use it.
Okay. And typically when you're using an API, why are you using it? What do you want from that company?
Some information around or something to do.
So what's this?
Integrations
Okay. Okay, so
between two types of services, so the developers should include it for each of whatever they're creating, and then other developers, independent developers, could use each of the APIs to connect or integrate their services somehow.
Okay, so the idea would be if a company were to provide an API, It's providing that because it wants to give a means for other programs to access their services, where their services could be, actual functionality, things, magic tricks they perform. It could also just be data that they have that they've either collected over the years or just provide or made up, whatever it is. But they've provided a interface for this stuff, right? And when we think about, when we first think about APIs in the world of modern software development, we're typically thinking about things like us, sending the Weather Channel our zip code, and it spits back a JSON document of our current weather or something like that, right? That's us requesting data. And one of the things we expect from modern APIs is that there's a consistent way of working with those things. So any of you who've gone to any of the hackathons with us, that's one of the main go-to things we do is we integrate with other people's APIs, right? And this kind of is related to this idea of a standard. We've talked about this idea of a RESTful API, right? So let me just quickly do this here. When I say something is a RESTful API, what am I really saying? What does that mean for something to be a RESTful API?
Follows a certain standard, and standard is what's get, push, put, delete.
Okay, so a RESTful API, just from what we've talked about in here, probably indicates there's some sort of standard, because we've been talking a lot about this idea that standards are important, right? If you don't have a standard, then all of a sudden, for every new thing you want to do, you have to learn a predefined way or a proprietary way of doing it. Okay, so we're all about standards. So RESTful API presumably is some sort of standard. And you mentioned it's built on top of an idea. You mentioned 4 functions. And what standard did those come from? RESTful APIs are, he mentioned four functions: get, post, put, delete. Who provides those 4 functions? HTTP. So RESTful APIs are, this is a modern standard. Modern standard to talk to a service using a very old protocol. That is HTTP. Okay, that's the protocol, that's the language. So protocol and the word language, they're synonyms. Okay, human beings, we say languages, so I'm speaking English to you. In the computer world, just to make it confusing, we call them protocols. Okay, so the HTTP protocol, this is the language that web browsers speak to web servers. And so what we've done is we said, you know what, that's been around for a while. Kind of seems like it works. You know what, it provides 4 functions. And it just seems like if we think about this idea of a service, so service providers, what kind of things might they work with? Typically, it's going to be the transmission of data. Even if they're performing a function for you, if I ask Google, for instance, Google's API to, let's say calculate pi to the 100th digit or something like that, it's going to do the computation on the back end. So I'm asking it to perform a service for me, but ultimately it's going to have to send me that answer in some sort of format, right? So it's, at the end of the day, it's delivering data for me. So when we think about APIs, it's all about requesting data and receiving data. That's our client-server model again. And at the same time, we already have mechanisms for requesting data through HTTP. And HTTP specifically supports 4 functions: get, post, put, delete. And historically, gets and posts were the guys used for webby stuff. But somebody said, you know what, we can really think about the way all data is communicated between an API, between applications, so the client application and the server application that has the API, can be defined in terms of these functions. So a get gets existing data. A post creates new data. A put updates existing data. And a delete deletes existing data. Every single RESTful API supports those 4 functions. They don't have to have access to all those 4 functions, but everything the RESTful API does has to be implemented in terms of those 4 functions, and those 4 functions have semantics associated with them. So whenever you are doing a GET, using HTTP's GET function to talk to an API, you might have 20 different endpoints all dealing with GET, and every one of those endpoints, assuming the person wrote it in a RESTful way, okay, every one of those endpoints should be about sending you data that already exists in their database or that they looked up for you. You know, they checked their records and found the current weather for Grafton, Wisconsin, or something like that. And then they give it to you. Okay, so you might have 20 different GET endpoints at a certain API, but they're all about giving you data. You might have 20 different POST endpoints, and they're all about you storing new data. So maybe one endpoint creates a user account. Maybe another endpoint, gives you a new activity, creates a new activity record, stuff like that. So I shouldn't have probably picked 20. So yeah, it's a very complex type thing where you have to save all sorts of different kinds of data. Let's see. So, let's go from a senior seminar perspective. I think Abe, something you were doing in your project is going to involve kind of recreating the idea of like a parse, right? We're not building parse, but effectively creating tools that allow you to talk to a database so that you don't run into problems in the future, right? That's part of your project. That's one of your proposed things. I'm thinking about the right paper, right?
Yeah.
Okay. So as part of that, you might have in your application, you might have 10 different types of objects you need to save related to your project. Well, each one of those on the back end of a RESTful API would be a POST endpoint. Okay, one is to save a user account, another one is to save this, another one to save that, so on and so forth. All right, puts, that allows you to update stuff, deletes, that allows you to delete stuff. Okay, so RESTful APIs deliver a standard way of talking to third-party data sources through the HTTP protocol. All right, so again, it's all about standards. Now, the POSIX operating systems, they provide a standard API as well. So they expose various, quote, endpoints, various functions that they're guaranteed to have. So those particular functions are guaranteed to be there in all POSIX operating systems. They take the same parameters, so there's a standard way of talking to them. We've already talked about standard I/O functions, no matter what kind of file something is, universal I/O rather, implemented through standard I/O. But these guys are guaranteed to be there. So when we talk about the API, the system call API, what we're talking about is the collection of POSIX standard endpoints, POSIX standard function calls that are in existence on every POSIX operating system and what they do. So these are service providers for you that you can ask for the operating system to do X, Y, and Z. Kind of make sense? So we're going to be solving a lot of our systems programming problems in terms of the standard things that the operating system provides for us, rather than the non-standard things that might be there on some operating systems, because then we have issues where certain programs don't just run out of the box. All right, so one of the things we're going to start exploring is this idea of standard system calls. Okay, so let me actually jump down to this part right here. So some of you have seen this before. Just look at a Hello World Linux assembly, because this is going to give us an idea on how system calls ultimately function with a operating system. And in this case, we happen to be talking about Linux, which we already know to be a POSIX compliant, right? All right, so how many of you remember seeing this from one of your earlier programming classes with me? I talk about it at some point, but we maybe have forgotten some of the details about it. All right, so let's go through this. So right off the bat, we already know this is a low-level language. This is assembly. Not something we really want to code in, but we certainly can appreciate the fact that all of our high-level languages ultimately turn into something like this, right? So when we write our C code, we write our C programs in here, and they get compiled using the GCC compiler, they'll ultimately turn into this under the hood. All right, so this is an example of using a system call. This is Hello World in assembler. All right, so first of all, for those of you who had we talk about this in the operating systems class, these are registers, right? Okay, what's a register? When I say a hardware register on a computer, what am I talking about? What do you think, Pebbles? That's an easy one. You should know what hardware registers are. Okay. All right, let's go ahead. Define registers for me. They go, who? Okay. Well, why is that a register, not a hardware register? And why would it take on... I'm not even sure if you know what you're talking about or not. I mean, the point is what you've said so far means you might know what you're talking about. I mean, it's not a great definition, and registers are pretty easy to define, so I suspect you don't know what you're talking about.
I don't know what register is.
But it is on the CPU. All right. All right, yeah, that's not even close.
Just a place of memory that's very close to the CPU that holds very important information.
Okay.
Crucial magic tricks.
Okay. So, is it fair to say that a hardware register is a variable made out of hardware, made out of memory? So instead of it being this synthetic thing where we think about this idea of a variable, it's a physical variable. We have a physical container that is a part of the CPU that we can throw stuff in, and as he pointed out, it's really fast because it's so close to the CPU. All right, so we have a whole bunch of hardware registers. The newer the CPU, the more hardware registers it likely has, because that's part of the evolving architecture of these CPUs. But these are some hardware registers here: EDX, ECX, EBX, EAX. So each one of these is a physical piece of hardware, a physical piece of memory that lives on the actual CPU that we can store something in. All right. So something we're going to see here is at the CPU level. Remember, when the job of a programming language is ultimately to tell a computer what to do, and we do at the end of the day that we tell it what to do in a step-by-step basis here at the assembly language level. But typically, we're writing our code in a high-level language. So when we look at it here, we're seeing each individual little baby step that's actually happening. So we're kind of seeing what's happening under the hood here and how programs are actually executed. So even though in Java we might say system.out.println hello world and magic happens, this is the actual magic. This is the list of magic tricks the CPU is actually going to perform. All right. So first line here, well, let's just point out the data section down here. So this is where our variables are in assembly language. So we have a string we ultimately want to spit out to the screen. It's called hello world, and this is how long it is. So we have the message and we have the length of the message. All right, those are just predefined things. Doesn't really matter for this example here, but this is what we're going to print, and this is how long it is. Okay, so now what we do is we effectively stage some data inside of 4 hardware registers. That's these first 4 lines here. So the first thing we're going to do is we're going to move the length of our string into this hardware register. We're going to move the actual string itself into this hardware register. We're going to move the number 1 for some random reason, seemingly, into this hardware register. But over here we notice that this is the file descriptor for standard out. Now we've talked about file descriptors. We talked about that everything in a POSIX operating system is a file, right? And we talked about 3 that pre-exist: 0, 1, and 2. Okay, 0 is standard input, 1 is standard output, 2 is standard error. Remember those 3 guys we talked about? Okay, they're built in. Okay. FD 0, 1, and 2, they're there. That's a POSIX thing, okay? So us moving a 1 in here is us semantically saying, I am planning on ultimately outputting the standard output, which is the screen. Okay, unless we redirect standard output, but that's not something we're doing here. All right, so, but arbitrarily what we're seeing here is we're just moving the number 1 into this hardware register. And at a glance, we might not know what the heck this means. All right, we'll talk about that here in a second. Go ahead.
Can you only have one thing at a time in hardware register? Because I see that it's using each line as a different hardware register that it's using.
Yeah, I mean, a hardware register is a container. So, think you have we have 4 Tupperware containers in the fridge, and if you put some mashed potatoes in one of them, probably don't want to go in and put cake in that same one. If you plan on eating the mashed potatoes soon, although that probably wouldn't taste as bad as it sounds like. It might be weird. If you really, you mix mashed potatoes with cake, that probably is not that bad.
If you have the correct amount of salt you need in mashed potatoes, then
It's gonna mess up the cake.
Yeah.
Sounds like you've thought about this.
I love
it. I've done the math.
Notice he was really focused on the potatoes.
I love mashed potatoes. I mean, I'm okay with cake as long as it's good cake, but I prefer them separate. Don't mix them. But yeah, treat each of these as a variable. So if you put something in a variable and then you put something else in that variable, you overwrote what used to be in there.
Okay, so then once it gets past the into the second move, it's moving 1 into EAX, so it's overriding 4.
This guy here?
Yeah.
It is. Yep. And we'll get down to that and understand why in a second. All right, so we're moving 1 randomly into EBX. Then we're moving 4 randomly into EAX. Now 4 actually corresponds to one of those system calls, part of the POSIX operating system's API. Okay, so the POSIX operating system provides a set of magic tricks, and magic trick number 4 is system right. Okay, this system right is a function. All right, so we're saying move the number 4 into EAX, which happens to represent the number for the function I want you to call. Move 1 into EBX, which happens to represent the output stream that I want to send this over. Move my message, which is the thing I want to print out, into ECX, and move the length of that message into EDX. So I want us to think about these 4 lines in terms of how all this stuff happens under the hood as staging. We are staging 4 different values into 4 hardware registers for some reason. Okay? They're not being used yet. We've just put them in there. We filled 4 variables up, and now we're just sitting here doing nothing until we hit the next line. All right? So the next line, this is when we actually call the kernel. Now, what's the kernel? When I say kernel, what am I talking about? Is it the fried chicken guy?
the kernel level mode that allows you to make the higher level calls.
Are you allowed to answer what's the kernel by saying kernel?
Okay, well that I didn't.
So what's the nature of the kernel? When I say kernel, what am I talking about? The OS. Yeah, I mean, the kernel is the actual operating system, as opposed to the distribution stuff, not all the text editors and crap like that that sits on top of it. So the kernel is the actual piece of software. In modern operating systems, these are usually microkernels, so it's the compressed, only the things that actually needs to happen down there at the hardware level that we don't want users messing with without permission. All right, so the kernel is the actual piece of hardware or software that sits between us and the hardware. So right here, we're going to go ahead and interrupt the CPU and call the kernel.
So
Now
it is entering like the kernel mode.
Yeah, the CPU enters the kernel mode. Yeah, so that's a fair statement. True. Go ahead.
The INT is standing for interrupt.
Yeah, interrupt. All right, so we're asking the kernel to do something. Now, it just so happens that as a low-level programmer here, writing Intel assembly code for Linux, we happen to know that Linux is a POSIX-compatible operating system, and therefore there's a few facts that we knew going in here that if we didn't have these comments out here, we may not necessarily be aware of. Okay, that is, the kernel, when we tell him that, when we say kernel go, the first thing he's going to do is he's going to go and check one of our registers. The register he's going to check is EAX. Okay, the kernel's going to say, okay, what do you want to do? He looks in EAX, he says, oh, you want to do system call number 4. He goes back and looks at system call number 4. Oh, that's syswrite. Think of that now as a function. How many parameters does syswrite take to work? 3. What do you want to write? How long is it? And where do you want me to write it? Those are the 3 parameters the syswrite function requires. Okay? We just happen to put those 3 parameters in some hardware registers, staging them there so that the operating system can go on its search to go and find them. Go ahead.
Is there like a standard where I guess how does it know which registers to look in?
POSIX. POSIX has that standard. Yeah, POSIX tells you where to put parameter 1, where to put parameter 2, where to put parameter 3.
Oh, so like that EDX is always where the length will be
Uh,
for something like this.
For something like this, yes, but it's because EBX is parameter 1, ECX is parameter 2, EDX is parameter 3, so parameter 3 for syswrite must be the length. Parameter 2 for syswrite must be the message. Parameter 1 must be the stream that you want to write it out, the file descriptor. All right, so the kernel immediately goes to EAX and finds out what the heck you want to do. It sees you want to do syswrite, so it says I'm expecting 3 parameters. The first parameter I'm expecting is the output stream, the file descriptor for the output stream, and I know I will find that in EBX. Why? Because POSIX tells me that's where I will find my first parameter. Okay, so the kernel knows I'm looking for 3 parameters. Why? Because syswrite was written for 3 parameters. So it's going to go and get the output stream, see from EBX. It'll get the message you want to write from ECX. It'll get the length of that message for how much stuff it needs to read, because that register ECX is, let's say it's a 64-bit register. You might not be taking up the entire 64 bits with your message. So you probably don't want to print out a whole bunch of extra zeros and stuff. You want to figure out how many of those things how many bytes to read in. All right, so we're going to go ahead and read in from EDX the length. Okay, so now we grab those 3 pieces of information. The kernel now can actually perform that system call. So it pulls those pieces of information out, performs the system call for you, however it magically does that. All right, and then it comes back to our program here. All right, now notice up here, EAX held the system call we wanted to perform. That system call then dictated how many parameters it required. All right, so we get down here, we're overwriting EAX, which used to have a 4, but presumably this guy is done because we've already asked our kernel to perform the action, right? So now our kernel now we're back. So we're going to overwrite the 4 in EAX with a 1. And 1 happens to relate to the system exit command. And then we're going to interrupt the kernel again. So now Pebbles, how many parameters does system exit take? Everything you need to answer that has been talked about in the last 5 minutes. 1? Okay, tell me why. And what is that 1 parameter? Who? This guy? Isn't EAX the actual system call that we want to make? So that's system exit. So I'm asking, how many parameters does this guy take, and how do you know? What do you think, Yetter?
Since it's kind of exit, I don't think it's taking any parameters.
Okay. Why?
We already called the kernel and did everything above. And since it's
Do these guys have anything to do with these guys? This magic trick, this ship has sailed. Okay, so that magic trick is done. So now we don't need to worry about any of these values anymore. So we're just going to overwrite EAX with a 1 instead of a 4, which dictates that our next magic trick we're going to perform a system exit rather than system write. So you've told me that system exit takes no parameters. I agree with that. Now you need to tell me why. How do you know it takes no parameters? Well, I could have. What if I had put a 5 here? Let's say 5 is something more complex that takes 12 parameters. I don't know if that exists, but let's assume it does. So just because I overwrote EAX, that indicates that the guy must not take parameters?
No. It's like what the system's doing, writing out.
How did you know this guy took 3 parameters?
And I'm just assuming that we look above and that we see that we're printing out to the screen, we're writing, and we're getting a link.
Okay, well, so forget about this part for a second. This was system right. That was that system right system call. How do we know that this guy took 3 parameters? Besides me telling you system right takes 3 parameters. How can you look at this code up here and suspect strongly that that guy probably takes 3 parameters? Go ahead.
We gave it 3.
We gave it 3 things. We staged 3 different values inside of 3 different registers. Okay, so here's parameter 1, here's parameter 2, here's parameter 3, here's the system call I want you to make. Hopefully I gave you all the parameters that you're expecting. Call system right, assuming the moon's aligned, and I didn't implement this wrong, and maybe system right took 5 parameters. I only gave it 3, now it's going to flip out. But in this case, I implemented it correctly, so I'm going to come back here. It's going to go ahead and grab its 3 parameters from the appropriate registers and move on with life. Now in this case, I'm performing a different system call. I'm performing system call 1, which happens to be sysexit. Now, first of all, we can think about logically what does sysexit probably do? Probably makes the program end, exits the program, something like that. And generally speaking, do you think that's going to require inputs, or is it just kind of die? Okay. Kind of think about the nature of that function probably doesn't require a whole lot of extra crap. All right, so it can just die. So we might suspect it takes no parameters anyways. But then we can look here and say, well, we also didn't stage any extra values inside of things here. So at the very least, let's hope it doesn't take any extra parameters. Or potentially, it took the same parameters as the other guy took, and we're going to give it the same values. That's a potential side effect. But the fact that we didn't stage any extra values up here probably indicates that whatever this system call is doesn't require any inputs. So then we're going to interrupt the kernel. We're going to interrupt the CPU again, call the kernel. The kernel is going to do the exact same thing it did last time. It's going to immediately look in EAX, find out what it is that you want to do. He maps that over to the system call system exit, recognizes that, oh, well, this guy doesn't require any parameters, so I'm not going to go and look for any parameters, which means that even if you had done some random crap up here, it wouldn't have gone and looked for it. You could have just loaded anything you want into any registers as long as it wasn't EAX. And then the program ends. Go ahead.
So how do we know that it's the system exit call instead of like the file description for standard output?
Because of where it is.
Okay.
Yeah, but I put syswrite in EAX. I put sysexit in EAX. EAX is the POSIX standard place to put the system call you're going to make. Yep, that's the place that the kernel will. I mean, from our perspective, we don't necessarily know. We're putting something there, trusting that this kernel, because it's POSIX compliant, will come and look in this exact spot every single time to find out what it is I was asking it to do. That's our way that's the way of the CPU communicating with the operating system, because they can't talk directly to each other. So this is kind of a, I guess the lowest level example of a singleton, right? What are we doing? We're taking a piece of information, we're sticking it right here and say, the operating system will find it. And he's going to have to come and but make sure you say that creepy to yourself. It will find it. Then don't break eye contact. Find it. All right, so
Saying it to yourself, but you shouldn't break eye contact.
to anybody else, actually that's even creepier, right? So you say it like really softly to yourself, like almost like a mumble, so other people can't hear it, but you just stare at somebody else while you're saying it. But do this in a coffee shop with strangers. I mean, these are just suggestions. I mean,
Good programming practice.
this is good programming practice. All right, so in any case, that's kind of an example at the low level of how we might talk to ultimately talk to the kernel to perform hello world. So let's flip back here. All right, so now we have some additional standard stuff that we're interested in. So for example, we've talked about we've talked about the idea, not specifically the full list of system calls, but we've talked about the idea that POSIX compliant operating systems provide a standard set of system calls. And it seems like what we just saw, that they're indexed 1, 2, 3, 4, 5, 6, 7, big list of guys where numbers add up to actual system calls, right? And then we need to kind of map those guys together, and that'll probably be in our documentation when we're writing our assembly code, which is probably why we don't want to write too much assembly code. We like making system calls directly. Well, now we have the GNU C library. Okay, so the idea is that we're likely not going to be spending a whole lot of time writing stuff just like this. So I wanted to look at this from the perspective of this is what's actually happening under the hood. Okay, so we can understand how the kernel actually interacts with the CPU. Right, this is what's happening actually under the hood. For us, we're going to be writing higher level C programs, right? Which means that we need to have C libraries that ultimately map into this. Because when I compile my C program for hello world, so when I do printf hello world, and it goes in and turns it into this, well, it's going to have to know what to do to turn it into this. So we have the standard C library, and this is more of a Linux standard than a Unix standard because it's the GNU is an open source project. So this is the GNU C library, and I think what is it? I think GNU stands for GNU is not Unix. That's what it stands for. It's an interesting. So GNU is GNU not Unix. It's a thing. It's kind of stupid, but it is what it stands for. All right. So in any case, this is the C library. And so this is going to be the standard Linux library that implements all of the POSIX system calls. All right, so when we want to do a system exit, we'll call the system exit C library from Glibc. And that guy will, when compiled, will turn into the stuff we just saw. So under the hood, it would turn that system call into move EAX1 interrupt x80. Make sense? All right, so here's our glibc, and this guy, as an example, might map to /lib/libc.so.6 as an example. So this would be a shared library. We can do an LDD command. So if I go out to the terminal and I type in man LDD, is it just LD? For the linker. This guy will show me in this example for a program that I want to run which libc was linked for that guy. So here, let me see if I can fake it here. LD vi grep libc. That command does not do what I thought it did. And several object files and libraries. Oh no, that's the actual linker. That's not what I want. I want the command that will look at a binary like vi and tell me against what C library was it linked. It is LDD. Maybe Apple doesn't have that. Oh, whatever, doesn't matter. But in any case, this would be an alternative way of seeing the C library that a program was linked against. So in Linux distributions, it should be the GNU C library, so it should be something that looks like this.
Would there be multiple libraries?
There could be multiple implementations of POSIX. So for example, if you're on FreeBSD, well, that guy would actually have GNU. If you're on an OpenBSD system, like the Mac OS here, so I guess we'll stumble upon that and see if this is the case, it quite likely is not using GNU, although it does have GCC. Yeah, so it has the GNU C compiler, but it might not use the standard GNU C library. Instead, it might use the normal Unix libc, which is still an implementation of the POSIX standard system calls. It just might have different system call names. So maybe instead of, just as an example, instead of sys_exit, maybe it would be sys exit. I don't think that's what it actually is. I think they're both sys_exit, but as an example, it could be that. They both ultimately map to the same POSIX system exit function. You know, that's a system call from POSIX, but we have now a C interface, a C API into that. All right, so this Glibc is giving us the ability to talk to our operating system. Now let's see, do I have the book on here? I do, and I say go to page 51. Let's see why I said to do that. Maybe there would be programs there we have to look at. All right, so here's header files. So let's actually talk about header files a little bit before we look at those too much, because it's going to be kind of an important back information. We got 2 minutes, right? So header files. Most of us started with languages like Java or more modern languages where header files aren't a thing. So how many of you have ever worked with header files? Okay, a couple of you. All right, what's the purpose of a header file? Why do they exist? Somebody just randomly decide, you know what, it would be a cool idea to have our have extra files. Go ahead.
Well, the only way that I know them is from the Swift C bridging header files, and that basically just allows you to use a C library in Swift, basically. So it allows you to use a library that isn't in that language.
Okay, fair enough. You know, Swift obviously has been around for like 5 minutes, right? And header files have been around for a little bit. So while that's how they're leveraged in Swift to allow us to use Objective-C libraries inside of a Swift program, header files actually came from something from a lot longer ago? Years and years and years ago, something like that. So here, I'm going to actually ask the question. This will be your quiz on Friday. How did one-pass compilers lead us to invent header files? How did one-pass compilers lead us to invent header files? Modern compilers are two-pass compilers. We no longer need header files, even though they're still commonly used. In fact, we're going to use header files in here. So they're still very commonly used because we've decided that they're actually helpful anyways. But we needed them as a result of one-pass compilers. So that'll be your quiz on Friday. Make sense? All right, I will see everybody then.